Okay, so we're going to do what's called the Friedel's Craft alkylation. Okay, and this is the substitution of an aromatic ring with carbon electrophiles. Okay, so what we're going to do is we're going to take our benzene ring and we're going to add an R group to it. Now, it doesn't matter what we're adding just any old R group, but it is an sp3 hybridized carbon that we're adding. We'll see an example later on where we're adding an acyl group, which is slightly different. But hopefully you'll look at that and it won't be unfamiliar to you, will it? First reaction we learnt, Cl2 plus AlCl3. Here, we haven't got Cl2, we've got RCl. So R is any carbon. So it could be CH3Cl, C2H5Cl, any carbon chain. But you can see we're going to be doing the same thing that we did in the chlorine and Lewis acid. So we're going to take our RCl, okay, and we're going to do exactly the same. We've got the lone pair of electrons in the chlorine. We're going to introduce our Lewis acid, okay, and we're going to form a bond between the chlorine and the aluminium of our Lewis acid. Okay, so that's exactly the same as we did with the Cl2 example. So again, don't think, oh my God, he's showing us yet more reactions. It's the same movement of the electrons. It's just we've got one different component in it. But the movement of the electrons is the same. And it's about, if you understand why the electrons are moving, then you'll understand that this is the same. So the electrons are moving because the chloride has electrons. The aluminium has the ability to accept those electrons. Once you then end up with your product, you've got a chlorine, which is positively charged. What we know about chlorine is it is one of the most electronegative atoms out there. It is not going to be happy with a positive charge. So anything it can do to get rid of that charge, it will do. So in this case, the chlorine can say, well, there's a carbon next to me, and I like electrons far more than that carbon does, so I'm going to take the electrons from the carbon. Which is exactly what it did last time with the chlorine. It was a little bit more of a, well, we're both chlorines, which one's going to have the electrons? But in this case, it's really clear cut. So we will take the electrons from this bond and give it to the chlorine. And what that gives you is R plus, and then you've got Cl, Al, Cl3 minus. Okay, so all it is again is it's just a way of generating an electrophile, a really strong electrophile, and this one is R plus. Now what you've done before though is if it's a primary carbocation, we know that primary carbocations aren't going to be particularly stable. But of course what we also know from this is that it can exist at this point, and at this point that R group is still incredibly electrophilic because the chlorine is just waiting. The moment it can grab those electrons, it will. So it's waiting for the aromatic ring, that electron density, to approach the R group. And the moment it does, the R group is lacking in electrons. They're being pulled away from it by the chlorine. And as soon as any other electrons appear, they are going to react with that R group. So although we might say R plus on its own, a primary carbocation, wouldn't exist, in this environment, because we have the Lewis acid, we can write R plus. Okay, but it's only in this one, and that's because we understand why we're writing R plus. It's there because of this very specific set of circumstances. Okay, so then we're going to take that R plus and we're going to do the same reaction mechanism that we've just done with the nitro group and we did with the chloro and we did with the sulfur trioxide. Same thing, it's just how we generate the R plus that's important. So we're going to take our aromatic ring and we're going to take our R plus, but what we've shown is we know that R plus comes from the fact that we've got the Lewis acid there and we've got this chloride. Okay, we're going to form a new bond across there. You don't have to put the dots in, I'm just showing you that's why my arrow is kind of pointing between the carbon and the R group. It's just to show where it's going. If you draw it straight at the R group, that's fine as well. But I'm just kind of using mine to show where that new bond is going to form. Okay, and then we've got our aromatic ring. Again, these bits over here, we haven't changed, we haven't done anything to. It's here that we've added the R group, and that means that the carbon that was down here has lost its electrons, so it gets the positive charge. And again, we can draw all those resonance structures in if we want to. I'm not going to, but just to be aware that they're there. And then very similar to when we did the chlorine, we had, you know, Cl minus, which has come from the AlCl3. Yep, that gives us effectively Cl minus. We can use that to grab the proton and we've added our R group. So, and you can see hopefully that is the same reaction mechanism. It's not a different one. Yeah, it's exactly the same bit that we've done. So the generic mechanism is the same in all of these. How you generate your electrophile, that's a slightly challenging thing. Okay, so as I said at the start, what about the kind of unstable carbocations? So what if we have something which we think, you know, well, we know a primary carbocation isn't going to be particularly stable. What happens? Well, you can consider it almost like an SN2-like reaction. The nucleophile is going to react with our electrophile, and that's going to allow the chlorine or the AlCl part to effectively be the leaving group. So you consider it like, it's not an SN2, but it's like an SN2. If you have something which is quite stable, okay, it's less likely to be like an SN2 because you might get some stereochemical clashes. If you've got a small nucleophile, a small nucleophile will easily fit into this space here, but with a big aromatic ring, it's not going to fit in there as easily. So that's unlikely to be SN2-like, in which case we consider it to be more SN1. That's when we would generate this actual carbocation. So this is just, again, an awareness. Okay, if you put RCl plus AlCl3 equals R plus, that's fine. I understand, and you understand that what that system generates is a carbocation. Okay, and we have an appreciation that if it was an unstable carbocation, it probably would react like the bit at the top. But if you're forming a secondary or a tertiary carbocation, it probably would be a formal fixed carbocation like at the bottom. And that's all this slide is saying. It's just to make you aware, but just showing R plus is what I need to see, what I need to see for your basic understanding. This is just to underpin that, to make you realise it's a little bit more complicated. But you know, we should be aware of it. Okay. So that's adding an alkyl group. That's adding this kind of CH3, an sp3 hybridized carbon. But we can also do an sp2 hybridized carbon. So we can try and add things which are slightly more difficult. And we can do that in a couple of different ways. So first of all, we can look at saying, well, any way we can generate a carbocation would allow us to do this kind of reaction. So here's an example where you've taken what is effectively at the start sp2 hybridized. So this alkene has got two sp2 hybridized carbons, but by changing it, by protonating it, for example, so doing the first step of your HBr reaction mechanism, you can form carbocation. And then that carbocation can do exactly the same reaction. We can take the electrons out of the ring, react it, go through a couple of steps, and add the alkyl group. That's a really bad arrow. Okay, we can do several steps then after that where we lose the proton and we get addition. Again, another example. Take the alkene to start with. Okay, so the alkene is here. We can protonate it by, again, adding a proton, acidifying it, generate it by protonation, and then we can do exactly the same thing. This can react with that carbocation. We can add an alkyl group. So that's one way of taking what looks like it shouldn't work because it's an sp2 hybridized carbon, but we can turn those into the sp3 hybridized ones. We can turn them into the carbocation we need. And just to go back and show, again, just an example of something which may not look like it would be able to generate a carbocation. You haven't seen many of these before, but we can take an OH group, we can protonate it again, we can lose water. We're going to cover all of this when we do carbonyl chemistry, the idea of protonating OH groups and losing water. So this will make more sense then. But again, it generates a carbocation. We can add that to our ring, so we can use the electrons. So that's just all I'm showing you there. I'm showing it quite quickly. It's just that you can generate carbocations from a number of different ways, and you don't have to just think of it as being RCl. There are other ways you can do it. You can do it from what looks like an sp2 hybridized carbon. You can do it from things which don't look like they would generate a carbocation. Okay. Now it's time to see whether that has sunk in at all. Go. So what I'd like you to do is look at this. This is just a simple example. How would you do this one? You've got a standard benzene ring and you've got an alkyl group. So this is equivalent to RCl, but in the actual example, AlCl3 or Lewis acid. Have a go at seeing whether you can draw the mechanism of that.